Welcome back. We've built the skeleton of a neural network with its layers and neurons. But right now, it's a lifeless machine. The spark of intelligence, the ability to make complex decisions, comes from a crucial component inside every neuron. Today, we're talking about activation functions, bringing your network to life. So, why do we even need another function? Here's the critical reason. Without an activation function, no matter how many layers you stack, your entire neural network would just be a very complicated linear model. It would be no more powerful than simple linear regression. Activation functions introduce non-linearity, which is the secret ingredient that allows networks to learn the incredibly complex, curved patterns found in real-world data like images and text. Let's meet the classic, the sigmoid function. It takes any number, no matter how large or small, and squashes it into a smooth, S-shaped curve between 0 and 1. This is incredibly useful for output layers in binary classification, because we can interpret the output as a probability. However, for hidden layers, it has a major problem known as the vanishing gradient, where the learning signal can become too weak in deep networks, effectively stopping the learning process. Next is the hyperbolic tangent, or Tanh function. It's very similar to sigmoid, another S-shaped curve, but it squashes values between -1 and 1 instead of 0 and 1. This zero-centered property often helps networks learn a bit faster than with sigmoid. However, it still suffers from the same vanishing gradient problem, which is why it's also less common in modern deep networks. Now for the undisputed champion of modern deep learning, the rectified linear unit, or ReLU. Its rule is shockingly simple. If the input is positive, the output is the input. If the input is negative, the output is 0. This simplicity makes it extremely fast to compute. More importantly, it doesn't suffer from the vanishing gradient problem for positive values, allowing for much deeper and more effective networks. Its main drawback is the dying ReLU problem, where a neuron can get stuck outputting 0 and effectively die. So with all these options, what's the rule of thumb? It's actually quite simple. For all of your hidden layers, start with ReLU. It's the most common and effective default choice. For your output layer, it depends on the task. If you're doing binary classification, a sigmoid function is the perfect choice to get a probability. If you're doing multi-class classification, you'll use a related function called softmax, which we'll cover later. And that's the spark. Activation functions are the nonlinear transformations that give neural networks their incredible power. By choosing the right function, we enable our network to go beyond simple lines and learn the true complexity of the world. We have the structure and the spark. But how does the network actually learn from its mistakes? In our next lesson, we will uncover the single most important algorithm in deep learning, the magic of backpropagation.